No? No student? Alright. Yeah, just want to realize like how the people are from. So that QR code is my LinkedIn. So if you ever somehow want to give me some feedback, just please welcome to reach me out anytime. Okay, let's get started. So yeah, just before we started, I just want to bring this up. So this is kind of interesting topic I saw, I think at least 2 weeks. It's called like Mobile Aloha. It's a project from Stanford, and it's a pretty interesting project that using the imitation learning to like mimic humans like behavior to do some like daily work. I don't know if you have ever seen this before. So you do something like this, and there's some failure videos right here, and just make me feel a little bit comfortable to see this failure video. So, anyway. So while it's very low, I mean, the breakthrough I think is the low cost, because as I remember, this kind of robot costs a lot, and this one only costs like 30K US dollar. You might think it's still expensive, but I think it's cheap enough to replace a 7-Eleven later, I guess. So it's open source, so anybody can like play around with it. So just want to bring this up. Just stay tuned. I think the next wave for robotics hype is coming after I saw this. Yeah. Anyway, so what is SLAM? So it's called simultaneous localization and mapping. And there are two main regions in this area. One is called Visual SLAM or VSLAM, and another one is Lidar SLAM. And Lidar SLAM has 2D and 3D, and today we're going to focus on the 3D SLAM. So these three pictures you can see on the right is the like Roomba SLAM. So it's basically a 2D SLAM that people or you might think before. Okay. And the one on the left is a result from VSLAM. You can see some texture on it. And the middle one is the 3D LiDAR SLAM. That's what we're going to discuss today. And so the SLAM is powerful because it can reconstruct a very high definition map for future localization and planning, which is I think it's a core for any robotics or self-driving project. So that's how essential it is. And this is this tree is my personal study note about how like SLAM developed. So there are some, you can see there is a VSLAM and LiDAR SLAM, and there are some open source right here or papers. Some of them might have no open source code on the GitHub, but anyway, I just figured it out. And I think I will convert these slides to PDF later, and if you are interested in it, just feel free to check it out. And so, okay, and there's some like sensor fusion stuff, like there's tightly or loosely coupled stuff, but today we're not going to cover that as well. So we're just focusing on the LOAM family, LOAM later. And machine learning is another topic, so we are not going to cover that as well today. So why LiDAR SLAM? Because LiDAR has very high accuracy and long range for a lot of users, make it more robust. Though it's expensive and it's weather sensitive, and for mechanical like lidar, the update rate is kind of low, so and has no velocity. But somehow they figure it out, so I just put a question mark right there. And there, like for 2D and 3D lidar, there are some like mainstream, like for 2D lidars, and you can see those four. And for 3D, there's like cartographer from Google, and LOAM from the CMU, and Leo is the LOAM with the IMU integrated. So I think these are the main three popular one. And the prerequisite knowledge. So before I get started, you might need to know this terminologies and tools like ICP and coordinate transform and Gaussian method and never, I don't know about that. I call it LOAM method, just for simplicity. So these two are for like nonlinear solver, and the tool will be, all this paper is going to use the tools below to run it, like using ROS and using Cirrus for nonlinear solving and Eigen for linear algebra solving. So let's start with LOAM. So LOAM is Lidar Odometry and Mapping in real time, and it like specify real time in the paper of the topic, so means it's very lightweight. It's published like a decade ago, and it's still the top three. It's still the top two lidar slam on the Kitty benchmark, so it's very impressive. No one can surpass them with like only 0.5% error on the translation, so it's very impressive. And the way they achieve this is to use the feature-based 3D lidar, like feature matching, to achieve this high performance. And it also split the SLAM into two threads. So the faster one is for lidar odometry, and the slow one is for the lidar mapping. And we'll cover that later. Oh, just if you have any question, just interrupt me anytime. So, and here's a pipeline. So you can see that. So once you get a point cloud from the lidar, and you'll use cloud registration to stack all the upcoming lidar point cloud together to the first frame, and then the lidar odometry will calculate the frame-to-frame transformations to get the odometry. And once you concatenate up to 10 frames, you'll send to the lidar mapping to reconstruct the map. And this is how it works. And we'll talk about some details later. Oh, sorry. Okay, so the feature extraction is I think the core of this method. So it will, like in traditional method, people use eigenvector, histogram, ICP, NDT, sort of like solar method, but those methods like consider all the points in the scene, so very computational heavy. And the proposed one is you extract the edge and the planar points from the point cloud to save the time. And it proposed this curvature formula. The x is the points in 3D space, and the s is the number of the point you're going to count. And the sum, you sum all the displays, all the nearby points, displacement, and then after this calculation, you've got the curvature. And so for low curvature, you'll consider it as a plane, and for high curvature, you'll consider it as h. So then we can move on to here. This is some of the rules they use, like pick the 5 point and prior points. So it's like 10 points for each collection, and you split the scene. So because for mechanical lidar it's like 360 degrees, so you split into 4 identical subregions. But well, in LOAM is the open source implementation. It's split into 6, but anyway, just have to split into a couple subregions, and each subregion can provide maximum 2 edges and 2 planes. So to save the computational cost, and you'll skip some like point is too close or parallel to the beam, or disconnected point. Like if the point is like, you'll skip the B point in this scenario, and you will skip the B and A in this scenario. So just to avoid like this kind of like situation, you might consider B or A is a feature, but it's actually not. And then once you got the feature and you calculate the feature between each two frames using this simple like distance from one point to a line or one point to a plane. So the first one is calculate this feature is how far from in this frame is how far from the closest feature line in the previous frame. Just I don't know if you can. So once you have this like distance, you can like know the transformation between these two frames and got the odometry data. And then, so it's using a constant velocity model, and then with these two formula, you can like combine these two formula into a single one like formula, and using I think I messed up the format, but anyway, use the LOAM method to solve the final formula here. It's a FT. I don't know how to say that, but solve the last function below from the above two equations, and then you can get the optimized translation between each two frames. And for the lidar mapping, you will extract okay, so for lidar, you will like, once you have the concatenate map from each 10 frames, you will try to, sorry. Yeah, so for the lidar mapping, it will just concatenate like 10 frames and then compare the feature between the map and the point cloud you just stick, and then try to fit the concatenated cloud to the map. But it's using like 10 times like feature points, and we only use the 10 meter cube area from the map for efficiency, so it won't like grab all the points from the map. And it's using the 3D KD tree to make it like process faster. And since in the map we don't have the feature anymore, so the way we extract the feature is using this eigenvector and eigenvalue to decide if a cluster is a H or a plane. So if it's H, there will be like one large two small eigenvalue, and for plane there will be like two large, one small eigenvalue, like the animation shows. Like in this case, it will be only one. Okay, plane will be like two large eigenvalue and one small eigenvalue. And for H, it will be like this, only one large eigenvalue. So with this, we can decide if a cluster is H or is a plane. And then do the same thing again, trying to match the features from frame to map, and then you can have the final like point cloud or map cloud, and then they also use the voxel to reduce the point cloud size, or the point cloud will be too dense. So this is how the whole framework works in LOAM.
Sorry, how did you decide which points forms a cluster?
There?
You have to find a cluster to find the proper eigenvalue and eigenvector to decide whether it's an edge or a plane, right? Mm-hmm. So, but how do you pick those points to cluster, to form a cluster?
So that's why it's using the 3D KD tree. You find the closest one.
So it's just like nearby points.
Yeah, so kind of like brutal force. So yeah, so you couldn't, if the frame to frame is too far, it might fail. I think that's the point.
Okay, so it's just a range thing.
Yeah.
So it's only considering how far the points are, and maybe, for example, taking the points within 10 meters and forms a cluster and decide whether if it's an edge or a plane.
Yeah, but because you have like couple features and couple planes, so that's why we introduced the I don't know, LOAM method. I don't know how to spell that.
Yeah.
Try to find the optimal like possible solution. Yeah, and yeah, I'll talk about that in later. There's a paper called Lego LOAM. I think you'll try to cover that. Yeah.
Thank you.
Yeah, that's a good question. So here's the conclusion of LOAM. So it's the very first feature-based 3D LiDAR SLAM, very lightweight and real-time usage. And it split the SLAM into odometry and mapping processes, which is very, I don't know, innovative. That's the word I come up to my mind. So it's fast and efficient, and only sparse map for memory saving, and academic level code, which is simple because compared to Google's SLAM, it's like a different level of API, and LOAM is very simple, just couple files, and anybody can easily like modify it. That's why many people paper based on LOAM. We'll talk about like two more later. And because it's only LiDAR SLAM, so you don't have to calculate any like sensor to sensor extrinsic, so quite simple. But the problem is it has no loop closure, so for a long range SLAM, you might face an issue, and it's not able to tolerate like fast rotation or like even translation. If it's too aggressive, it might fail. The planar feature is not very good for ground vehicle. We'll talk about Lego LOAM later. Lego LOAM is for UGV optimized application LOAM. Here's the I don't know how to play video on iPad. Alright, I was trying to show the demo. If we have time, I will show you later. Okay, so VLOAM is the second paper they published the next year by the same people, the Jizan and Sanju. Oh, by the way, Sanju was my previous boss. I was working in neuroastronomy, and he found the company, the Sanju, and by using VLOAM as the core like product of our company. Yeah, so so in VLOAM they introduced the image feature with depth information. They kind of like just project the LiDAR point on the 2D image feature to have a better, higher frame rate. So some of you might know the computer vision. So it's using like Harris feature extraction and then the optical flow tracker and with LOAM. And here's a pipeline, a little bit more complicated than LOAM, but not that bad. So they basically just put the visual odometry prior to the Lidar Odometry. And they combine the original LOAM into the Lidar Odometry and Mapping together on the right hand side. So there are like three kind of different features for VLOAM. So will be a feature with depth data, and a feature with depth data by triangulation using the previous motion, and a feature without that. And I'm gonna skip the data processing, so it's just basically like pre-processing the data to make sure it's in front of the image. So I'm gonna skip that. So it basically just find the, so for feature association, means frame to frame like feature association, you'll find the closest 3 points from the depth map and try to compare them if they're the same feature, and then you'll calculate the distance from the 3 point. So 3 point you have a like planar patch, and just calculate the distance from your camera to that planar patch, and then to get the distance. And for tracking feature, but suddenly lost their depth information, you'll use the traditional like triangulation, like I think it's called P3P, or I mean you have like 5 point or 8 point for feature to find the transformation between two images. Use like, but because you have like previous depth data, so you can recover the scale. It's called structure from motion, by the way. Yeah. And then here's on this image you can see the green dot is the first feature, like the feature with depth data, and the blue one are the feature with the data but by triangulated transformation, and the red one are the feature without depth data. And here's the reason is that because the LiDAR has like a limited range, so for further feature you cannot like get the depth information from them because it's too far. So all those things you can do is just use like traditional computer vision way to get the coordinates. But for near features, it's easier for you to get the depth data. And here are the two core equations for VSLAM. So for a feature with depth data from the depth map, you can use these two functions. So it's basically just a traditional, like, how to say that, the projection formula x is equal to r x plus t. That equation. So, but it's split into like three different. It like expand the matrix, but since you have no scale to the z-axis, if you are using, you have no idea about the scale. So you put the, I don't know if I can show you. Alright, I shouldn't have used iPad. Anyway, so I have a slide that's showing the whole equation. So anyway, just use these two equations to calculate the feature from transformation from frame to frame. So for different feature, use different equations. Then use the again use the LOAM method to solve the 6 degree of motion with the equation above. And you will assign the residual to each feature and then optimize it later. And then since because visual odometry is tend to drift, so you use a linear like drift correction formula to fix it. And the rest of the formula and equations are the same as the LOAM. So you'll see the f function again, but with the drift correction. So yeah, so that's pretty much it. Just to introduce the image features and to achieve like a higher 60 Hertz odometry update rate, and still with the 1 Hertz mapping rate. So you can get a higher frequency and still keep the higher accuracy. And the problem is that if the visual odometry like got messed up, and your result is going to be very bad as well. So it's very like texture and scene sensitive. And also you need to calibrate the sensor. You need to get the extrinsic. I don't know if I can play the video here. Oh yeah. Alright, anyway. I think I'm running out of time, so I will quickly cover the Lego LOAM. Yeah, so Lego LOAM is the one I was talking about. It's LOAM for ground vehicle version. So it also introduced the loop closure to avoid the error accumulation, and it's also open source. The previous two paper are not open source because they found a company and they closed the source. But this one, they're still in a university as a professor, so the source is open. And the pipeline is slightly different, but with a segmentation right there. And I think the major difference is the feature extraction part. We'll cover that later. So there are 5 major modules, and we're going to cover the first 4. And the last one is more like an optimization with LOAM method again. So yeah, consider. So what it uses is it convert the point cloud into a depth image. So for the resolution about like 0.2 degrees and 2 degree vertical and 0.2 degree horizontally, you can have like 1800 times 16 resolution for your image. And you will use the ground point segmentation like right here. So if the alpha right here is too large, you consider it as a normal point, but if it's less than the specific degrees, and you consider it as ground. To separate the ground. Okay. And to cluster other like object, it's using this kind of method. So for each point in the depth image, you will find the four near neighborhoods, and if their angles is less than 6 degrees, and they're the same cluster. It's from another paper. I put the reference down below. You can check there. The GitHub is open source, so yeah, you can see the video of that. So this is the point of depth map I was talking about. They project the lidar into a image, so it's like 18,000 times 60. So yeah, and you only consider the point that the cluster that have more than 30 points for LOAM. And feature extraction, again, the same formula as long. Now they, instead of like splitting the point cloud into 6 regions, it split the image into 6 images. And each sub-image have 2 edges and planars as well, again. So the feature matching is almost the same instead, but they use 2-step LM optimization to reduce the computational cost. So they first like focus on the planar features and only take the pitch and roll and the z-axis transformation for optimization. Because for ground vehicle, these are the only 3 factors you are care about. And once you have find the result, and then you use the x, y, and the yaw angle to estimate the H feature, and then fuse the result above. And this can, of course, you can still use the 6 degrees of freedom optimization, but the author says by split it into 2 different methods, you can save up to 35% of the computation time. Let me see if there's, and I think the interesting part of the mapping is that it split instead of using the whole entire huge map, it split each feature set, they take the feature set individually. So you can have this, and each feature set have its like post data and their points, so you can run the loop closure later by checking those sets. If they're like close to what you used to be, then you run an ICP to close the loop. Sorry, I triggered the series. So yeah, this is and to close the loop, it used this thing called ISAM2. It's an open source code again as well. So it's using the Postgres/LAM. So it's a little bit complicated. So I'm running out of time. So I will upload the PDF file later. So if you got a chance, you can check it yourself. So yeah. So if I introduce the 2-step LM optimization, it's a little bit faster, and split the map into feature sets, enable the loop closure implementation. So that's the two major improved part it did. But it's only for ground vehicle usage. So if you're using on the drone, you'll have some issue because the ground segmentation is affect the result of the drone. And here's a short video of the LOAM running on the Kitty dataset. No, not Kitty dataset, I don't know. And here's the result of the LOAM right here. yeah, conclusion will be LOAM has various modifications due to its simplicity. Like I said, the code is easy to read. So if you guys ever have a chance, just give it, just clone it and play around with it. And then introduce a 3D feature from point cloud, and which is very efficient for real-time usage. And the Leo series will be interesting part to check it out. So if you have IMU and you want to see if you can improve your odometry data, just feel free to play around with it. And yeah, that's pretty much it. Thank you. Any question? All right. If no, then we'll have a break for 10 minutes. And next one will be Nicholas. He'll introduce the RTK GPS application, and yeah, just stay tuned.
不好意思啊，我来打断一下，因为我差不多要回去了。就是我相信在座的各位应该不知道我是谁，不重要，因为我想要简单自我介绍一下。那如果有兴趣的，趁我在回加州之前，如果有兴趣可以跟我聊一下。我自我介绍一下，我叫浩志，然后我之前是在Rust 这个社群是我创的，然后我之前在 ETH 就是苏黎世联邦理工读硕士，然后后来毕业之后我进的是 Sony AI， 我 Sony AI 是第一个成员，然后我们做了 reinforcement learning 去做Ground Turismo， 如果你们有 PS4 的话 ，Ground Turismo Sport 上面的跟人竞赛的 agent， 然后我们赢过 agent， 然后我们的结果 publish 在 Nature 的封面上面，然后我名字也在上面。然后接着我加入了小鹏机器人去做那种4组跟2组的 robot， 然后接着我现在在 Apple 的 Vision Pro 的部门因为做演算法开发，然后很感谢Wen-Yu今天邀我过来看一下大家现在在做，就是这个台湾这个产业在做哪些事情。然后康欣学长是我以前在成大宏泰的时候认识的一个很强的同一个类的学长，他也很厉害，所以可是因为我今天早上去做手术，所以没办法这边待很久。所以如果可以的话，等一下给大家，如果你们有兴趣想要了解一些国外的产业啊 ，Robotics 啊，我在这边会再待10几分钟，如果有兴趣可以来聊一下，要不然的话我等下就会先回去这样，对，不好意思，对，谢谢。